Hi, my name is Charlotte Cotter, and I will be presenting the first part of our presentation entitled Linked Data and BIBFRAME. With the rise of the internet and digital data, information organization has undergone a number of important developments. In this presentation, we will be talking about the semantic web, linked data, RDF, and BIBFRAME. These developments continue to be at the cutting edge of conversations about information organization today. First, we will talk about the semantic web. So what is the semantic web? The semantic web is an extension of the current World Wide Web. Sir Tim Berners-Lee, who is credited with inventing the World Wide Web, first articulated a vision for the semantic web at the first World Wide Web conference in 1994. The idea became widely popularized by an article Berners-Lee wrote with colleagues for the journal Scientific American that appeared in 2001. Currently, the semantic web is also promoted by the organization World Wide Web Consortium, abbreviated W3C, of which Berners-Lee is a key player. But what exactly is the semantic web? We can start to answer this question with a quotation from the seminal 2001 Scientific American article. The semantic web will bring structure to the meaningful content of web pages, creating an environment where software agents roaming from page to page can readily carry out sophisticated tasks for users. Let's break this down a little bit more. To understand the semantic web, we have to start with the idea that the current World Wide Web is made up of documents that are connected to other documents. While these documents hold a great deal of information that is human readable, this information is not accessible to machines. For instance, while we might see a webpage of a doctor named John Smith and gain from it various information about his practice, the machine cannot access this information, since most of what it is told is about the webpage layout and formatting. The semantic web envisions bringing meaningful, machine-readable content to web pages through definitions of key terms and rules for reasoning about them logically, so that computers can process them. With this infrastructure, people will be able to rely on highly functional agents to conduct certain tasks, like automation, integration, and reuse of data across various applications. Agents are computer programs that rely on observing patterns to perform various actions autonomously on behalf of the user. Why the semantic in the semantic web? Semantics refer to meaning. Meaning becomes important in two ways in the semantic web. Firstly is the ability for the computer or machine agents to, quote unquote, read meaning into information or data on the internet as described above. Secondly would be the ability for these agents to communicate meaning effectively with each other. These agents must be able to locate information resources on the web and combine them in meaningful ways to perform tasks. They also need to recognize, interpret, and respond to communication acts from other agents. A crucial part of clear communication is ensuring that both agents involved understand the same meaning for the terms used. We cannot assume that other agents will use the same terms, or that if they do, that the terms will mean the same thing. For instance, it is not sufficient to rely on shared cultural understandings of concepts such as creatorship. To avoid confusion between independent and possibly conflicting definitions of the same term, each agent needs to declare exactly what terms it is using and what the terms mean. This specification is referred to as the agent's ontology or vocabulary. The vocabulary defines and clarifies the concepts and relationships used to describe and represent an area of concern in formal machine-readable language. Ontologies also typically define types and relationships, as well as a set of inference rules that allow the machine to manipulate the data in ways that are meaningful to humans. What are the aims of the semantic web? What could the semantic web do for us? Well, in the digital realm, the semantic web would allow for information to be surfaced by machines in the form of data. It would allow for greater data reuse by making data available for purposes not planned by the data provider or within the original application. It could increase interoperability between systems through vocabularies and ontologies. Finally, it could reduce human processing, which can be costly in terms of time and finances. The semantic web may also have an impact on our daily lives. The example given by Berners-Lee and colleagues in the 2001 American Scientific paper would be two siblings trying to locate a specialist and coordinate physical therapy sessions for their mother. In this scenario, both siblings would be able to rely on agents to research and coordinate information on providers in their areas and user reviews of these providers, and then to integrate that information with information about their schedules, their insurance coverage, etc. This sounds like a great service, but it still may be a ways off. Although there are projects that use semantic web ideas and technologies, the semantic web as proposed above is still currently in development by Berners-Lee, W3C, and others. Today, much of it is still an abstraction. Nevertheless, the semantic web remains an important development to watch. Our next topic is linked data. Linked data is at the heart of the semantic web. Tim Berners-Lee first coined the phrase linked data in 2006 when talking about the design of the semantic web. In 2009, Berners-Lee featured linked data in a prominent TED Talk entitled The Next Web. Most generally, linked data means publishing data on the web that links to other data on the web. In the traditional web, documents, usually web pages, were linked to other documents, but individual pieces of data within the documents were not linked. Linked data is when these individual pieces of data are linked together to provide richer information about things and concepts. One of the most important features of linked data is that the data being linked may very well come from different sources, for instance, applications from different organizations, creators, or disciplines. Linked data is importantly machine-readable data that is explicitly defined and linked to other datasets, which are in turn linked to other datasets. Tim Berners-Lee outlines 4 principles for linked data, which essentially amount to use URIs as names for things, provide information about those things at the URIs, and link those URIs to other URIs. URI stands for Uniform Resource Identifier. A URI is a distinct string of characters used to unambiguously represent something. This could be something on the web, but it could also be a person, place, or thing, or even a concept or idea. URLs are a type of URI that most people are familiar with. URLs point to a specific location on the World Wide Web. However, although URIs may take a form that looks like a URL, not all URIs lead to an actual website. What do URIs do for us? There could be a URI to represent a person named John Smith, for instance. John Smith is a common name, so this URI would help disambiguate this particular John Smith being talked about. It would also provide a standard place on the web for anyone who wanted to talk about this particular John Smith to link to. What does linked data hope to achieve? The major example cited by Berners-Lee in the 2009 TED Talk is that linked data would allow researchers to come out of silos and ask new and interesting questions that bridge across disciplines in order to solve the problems of our time. But linked data may also be in our daily lives. Social networking sites are always using data about our relationships, but you can't use these relationships across different social networking sites, as the picture on the slide depicts. So information about certain people are stuck in their individual silos. Linked data would allow for interoperability between these different sites. In that sense, linked data is about creating links between data that bridge traditional silos in order to increase data reuse. In order for linked data to be realized, there must be a standardized knowledge representation language for these linkages to be in. That is where RDF comes in. RDF stands for Resource Description Framework. It is the standard knowledge representation language for the semantic web. RDF can be used to make assertions about things both on and off the web, and also to make statements about links between these things. Importantly, RDF is also designed to be domain neutral. In these ways, RDF creates a common infrastructure for the creation and publication of structured data on the semantic web. For a little bit of history, the first version of RDF was published as a W3C recommendation in 1999, and it was followed by a revision in 2004, which sought to provide a formal foundation for the more expressive ontology language OWL. In terms of structure, the basic model of RDF consists of resources, properties, and statements. Resources refer to all things being described by RDF expressions. This may be an entire web page, a part of a web page, a whole collection of websites, or an object not directly accessible via the web, for instance, a book. Properties are specific aspects, characteristics, attributes, or relations used to describe a resource. A statement is a specific resource together with a named property plus the value for that resource. Now, RDF statements come in the form of RDF triples. Each triple contains 3 elements, a subject, a predicate, and an object, which are described by the W3C primer as follows. The subject is the part that identifies the thing the statement is about. The predicate is the part that identifies the property or characteristic of the subject that the statement specifies. The object is the part that identifies the value of that property. It could be another resource that is connected in some way to the subject, or it could be a value associated with the predicate. These statements should be read in a directional way from subject to object. In the blue graphic on the top right of this slide, you can see the structure of an RDF triple in graphical form, which can be read as a subject has the property of a predicate with the value of an object. Therefore, an example of this kind of statement could have Hamlet as the subject is written by as the predicate and Shakespeare as the object, which would be to say that there's a resource, Hamlet, that is written by Shakespeare. However, to be readable by machines, we are not using natural language for the triples. Rather, the subjects, predicates, and objects are represented by URIs. The object also has the option of being a literal, however, the subject and predicate may not be literals. URIs are the universal resource identifiers discussed earlier. Literals are values such as character strings, numbers, or dates, which will describe the subject, such as describing the name of a person or the date of an event. The triple structure is sometimes described in terms of a graphical structure, where the resources are nodes and the predicates are edges or arcs. You can see on the bottom right an example of a simple RDF triple expressed with URIs. This is taken from W3C's RDF primer. Here, the top green circle is the subject, referring to an example website at this location, http://www.example.org/index.html. The predicate is the creator element from Dublin Core. The object then is the URI for a certain John Smith in this particular example. Thus, the totality of this RDF statement is this example resource has a creator whose value is John Smith. In other words, John Smith is the creator for this resource. But RDF doesn't stop with a single statement. For one, we can say much more about a resource, such as the date it was created and the language it is in. We can also go back and give more information about John Smith, such as his address or his occupation. And then, of course, John Smith and his resources and such can be linked to other resources and people, which themselves can be described and linked in turn. A set of RDF triples, as seen on the right-hand side of the slide, is referred to as an RDF graph. The idea here is that these resources would have attributes and relationships to other resources, which in turn would have their own attributes and relationships, and so on and so forth. The vision would be to eventually create a graph of these relationships and attributes at a truly massive scale for everything that exists on the web. A couple of last things. RDF can be expressed in the XML syntax, where it is also called RDF XML. There are also other syntaxes that can be used to represent RDF, such as Turtle and N3. RDF has two accompanying ontology languages, which are languages for defining RDF vocabularies. They are RDF Schema and the Web Ontology Language OWL. RDF also has a query language known as the Sparkle Protocol and RDF Query Language, or more simply, Sparkle. In conclusion, there are many complexities to RDF, the semantic web, and linked data that we do not have time to discuss in this presentation. In fact, it may be that one of the barriers to widespread adoption at this time is in their many complexities. However, even so, we can see that the ideas surrounding the semantic web, linked data, and RDF point to new developments in the realm of digital information organization. As our lives and world become increasingly digital, the library information science profession is exploring ways to integrate their work and data into these developing frameworks. BIBFRAME, which Shawna and Lyette will discuss, is a key example of the LIS profession's current engagement with this movement.
Hi, I'm Lyette Mercier, and now we are going to talk about BIBFRAME, which is the abbreviation for the Library of Congress's Bibliographic Framework Initiative. BIBFRAME began in 2011 when the Library of Congress contracted with the data management company Zephyra to develop a new model for creating and sharing metadata using RDF and linked data principles. The initiative's ultimate goal is to build a model that can replace MARC as the accepted cataloging standard for libraries. But BIBFRAME's objectives go beyond simply replacing MARC. It also seeks to move away from MARC's reliance on self-contained records about individual resources and towards linking data across resources, reducing data redundancy. The 2012 Library of Congress report, Bibliographic Framework as a Web of Data, Linked Data Model and Supporting Services, also envisions BIBFRAME as, quote, the foundation for the future of bibliographic description that happens on, in, and as part of the web and the networked world we live in. It is designed to integrate with and engage in the wider information community while also serving the very specific needs of its maintenance community, libraries, and similar memory organizations. To put that quote in simple terms, it seeks to take the information currently siloed within library and memory organization databases and make it accessible via anywhere on the web. A quick note on terminology. In 2017, after extensive experimentation on and revisions to the original 2011 model, the BIBFRAME 2.0 vocabulary replaced the original BIBFRAME vocabulary. The project as a whole is still referred to as BIBFRAME, but the vocabulary and ontologies is BIBFRAME 2.0. So you will see both of those used. The goals of the BIBFRAME initiative, as stated by the Library of Congress, are to differentiate clearly between conceptual content and its physical digital manifestations. This first goal is closely related to the IFLA LRM model's classes that distinguish between the conceptual, works and expressions, and specific, manifestations and items. BIBFRAME differs from the LRM model by only having 3 classes in its hierarchy. Instead of WEMI, it uses work, instance, and item. The Library of Congress defines instance as a work may have one or more individual material embodiments, for example, a particular published form. So instance maps most closely to manifestation, and expression is not really used in BibFrame. The second goal is to unambiguously identify information entities, e.g. agents. BibFrame 2.0 has 3 key concepts that have relationships to the core classes. These are agents, subjects, and events. The second goal recognizes that BibFrame records must clearly identify agents responsible for each resource's creation, including authors, publishers, composers. This aligns with the IFLA user task identify, which specifies that users should be able to clearly understand the nature of the resources found and to distinguish between similar resources. This third goal, which is underlined because it is the majority of what we're going to be talking about on the next slides, is to leverage and expose relationships between and among entities. You'll recognize it as a version of the goals of linked data. The BibFrame model uses RDF triples and URIs in building its records so that they may be linked to other records, creating a web of data and allowing users to discover connections between resources that they might not have otherwise. So what exactly is BibFrame? Well, first of all, it's a work in progress. Standards and tools that can be used to implement the BibFrame vocabulary are still being developed. As of 2020, libraries are not actively converting from MARC to BibFrame. So what we're covering here are programs and tools that are being used to test the BibFrame model in order to refine both the model itself and the tools around it to a point where they can be used in large-scale conversion. All right, then we have the Jude quote, which is, the BibFrame model describes the structure of bibliographic resources and their potential relationships. So as I said before, BibFrame uses RDF triples, URIs, and specialized vocabularies called ontologies to give resources a common infrastructure that makes it possible to reveal and link relationships between these resources. It builds metadata that may be linked, searched, and shared throughout the internet as a whole. BibFrame builds records by using RDF triples, examples of which you can see in the diagram here. So if you were talking about the novel Ulysses, a triple could be work, Ulysses, has agent, which you'll see is the little arrow at the top there, and then James Joyce. So you would have a URI for Ulysses, a URI for has agent, and a URI for James Joyce. And because of that URI for James Joyce, that could be linked to Joyce's other works, as well as related works and scholarship about Joyce that might not come up in a traditional title author search. We'll see a little bit more about that later. These linkages will also help patrons more easily locate physical items. Non-linked records can only tell a patron if the one institution whose database they're searching has a copy of the item they need. Linked data could not only show you that the item exists, but where out of a multitude of institutions it's located. So now we are going to talk about some of the steps that are being taken to move BibFrame from a theoretical model to a working one. So the first thing we're going to talk about are BibFrame editors, which allow users who maybe aren't as familiar with the framework or with the ideas behind linked data to get an example of what building a record would look like. So at bibframe.org, you can view and even edit sample records, which you will see here. It's a very easy and intuitive interface. Okay, here you will see that you can click on most of the things here. If you click on anything that is highlighted in blue, it will actually take you directly to the RDA toolkit where you can read the rules and standards there. And here, for example, if you click on primary contribution, it will give you the options that you would get from the RDA toolkit for person, family, corporate body, jurisdiction, or conference. And when you click on person, it will give you the option to search the Library of Congress name authority file directly. So one of the nice things about this editor is that it brings together and links multiple cataloging resources to make building a record easier. As you can see here, you don't see any of the code, any of the actual RDF triples, as you're working to build the record. But when you finish, you can hit preview and it will actually show you what it looks like. At the top here, you have the ontologies that are being used, and then you have the actual URIs and RDF triples that make up the record. So another BibFrame editor that is available is called Sinopia. It is intended to help library professionals build familiarity with linked data environments and collect data for developing further BibFrame tools. It's produced by the Linked Data for Production, LD4P project, which is a collaboration between Columbia, Cornell, Harvard, Princeton, and Stanford universities and the Library of Congress. It has been funded by grants from the Andrew Mellon Foundation since 2014 and works on standards and workflows for linked data production. As you can see in the diagram on this slide, LD4P focuses on building models, tools, workflows, and communities. In this case, it shows it solely for from resources to metadata, but currently LD4P is also working on resources to take from metadata to discovery. The current iteration of the project LD4P3, which began in July 2020 and is scheduled to end in June 2022, quote, aims to close the loop to create a working model of a complete cycle for library metadata creation, sharing, and reuse. Share VDE, which stands for Share Virtual Discovery Environment, is linked on the slide here and in the handout, and is a great way to see what linked data searches will most likely look like as BibFrame begins to be adopted. It connects the catalogs of a dozen major institutions, including the Library of Congress, Yale University, and the University of Alberta, making it essentially sort of a linked data mini environment. So one of the things that is working on behind the scenes is the ability to mass convert MARC records into BibFrame linked data, which is difficult because the models don't map exactly. Its user interface is an example of what a linked data search can look like. We're actually going to do a little one right now. You're given the option to search by person, work, publisher, or subject. And you'll see here, we're going to search last name first for Joyce James. And you can't hit return, you have to pick one of these records. So it's not really going to give you the immediate gratification of doing a traditional author search where whatever you get on the search comes up. You have to actually pick one of these. So as you can see, there are quite a few redundant records. If we go down here, we have Joyce James, comma, with parentheses. If we go next, we have Joyce James, comma, without parentheses. These, as you can see from the numeral, are all the same record. And if I wasn't sure that these dates were correct for the author of Ulysses, if you scroll down a little further, you get Joyce James, Irish author. Oh, okay, we'll click on that one. So we will wait for that to load up. You will see here that this is an excellent example of a robust linked data search. There's an image, a biography from Wikipedia here. We have other name forms, including in different languages. And if you scroll down to works, there are numerous works from, about, and inspired by James Joyce. Specifically, we're going to look at, here's the Ulysses. This gives us a list of records for items that are copies of Ulysses. You can find them at Duke, at New York University, and that continues for many pages. If you go back, you will also see that there is a separate record for Ulysses, a review of 3 texts, proposals for alterations to the texts of 1922, 1961, and 1984, which is an academic work about Ulysses, which, as you can see, is separated and not in a traditional list of titles the way it might be, an undifferentiated list of titles, the way it might be in a traditional title search. And then the third one I wanted to show you is called James Joyce's Ulysses in Nighttown, which is a transformative work inspired by James Joyce that is also showing up on his author search. We put the link to this record in the handout if you want to explore further. There's a lot of really interesting stuff on Share VDE. So, believe it or not, we have actually just scratched the surface of the developments happening with the BibFrame model. There are many individuals and groups working to make it a viable linked data cataloging system. To see more, you can explore any of the sites linked to on this slide, or go to the Library of Congress BibFrame websites and go through the latest tools and downloads listed there, including a Mark to BibFrame conversion viewer. Thank you.
Hello, my name is Shawna Banducci, and I'm going to be discussing the future and challenges of BibFrame. The future and challenges BibFrame presents are widely discussed throughout various webinars and articles. A quote from the article on the BibFrame Basics, a crash course workshop from earlier this year, explains from breakout sessions. The consensus was that everything takes a long time in the library world, and by the time BibFrame is implemented, everything else will have been moved forward. Interestingly, in a webinar talk on BibFrame, Beyond Mark, BibFrame and the Future of Bibliographic Data, given by Emily Duss-Nimscont in 2015, she estimates that it would likely take at least 5 years to totally or at least mostly make Mark a thing of the past. As we are now in 2020, and at the 5-year mark pointed out by Nimscont, BibFrame still has a long way to go before any wide-scale implementation could occur. In the future, catalogers' roles will change. As Nimscont also said, our roles may shift from being creators of metadata exclusively to being evaluators of metadata, identifying and figuring out what other resources is on the web that may have data that can be linked to ours to serve our purposes, which is a part of the challenges BibFrame will face that will be discussed later. There is no concrete timeline for BibFrame to become the standard, as converting the large amount of existing MARC legacy data to a linked format will take a significant amount of effort and time. The future of BibFrame is largely dependent on the utilization of the framework by those in the field. It will be important for cataloging librarians to change cataloging habits to fit the new tools developed for BibFrame. However, there is a lack of consensus in replacing MARC by library professionals as the standard encoding and data interchange format, and makes the future of BibFrame unclear. This fact only further exacerbates the challenges BibFrame will face in becoming the implemented standard. As stated earlier, an intensive challenge to BibFrame will be the need for mass migration of MARC legacy records and a large-scale buy-in of BibFrame by librarians and institutions alike. Linked data records will need to be created for BibFrame as a standard to succeed, which, as previously alluded to in the Nimscont quote, the resources, BibFrame bibliographic data, needs to exist on the web to be utilized. Actual utilization of said data becomes difficult as there is minimal software available to implement, maintain, and use BibFrame data. As there is minimal need and usage currently, there is little incentive for library systems vendors to incorporate BibFrame compliant software within their systems. A further challenge in implementing BibFrame is the flexibility of BibFrame as a standard. As noted in Benefits and Challenges of BibFrame, cataloging special format materials, implementation, and continuing educational resources, BibFrame is in principle designed to be a standard agnostic, which, while increasing its extensibility, may also result in an uncertainty of its application in specific cataloging contexts. By allowing for more open-ended usage, catalog records could result in errors and a lack of accuracy within records. Combined with widespread inoperability of other standards, BibFrame's translation process is complicated by semantic ambiguity within record fields, and issues arise based on library-specific data. Implementing BibFrame in the US alone is a significant challenge, as there are major issues of compatibility between schemas within US libraries. Unfortunately, there is not a single ontology or standardization that represents everything libraries or institutions want to express. Authors Park, Richards, and Brenza, in the article Benefits and Challenges of BibFrame, decisively sum up the future and challenges of BibFrame. Despite the promise of improved data management, sharing, and usage offered through the BibFrame model, There are a large number of serious challenges that must be overcome for its adaptation within the library community.